New study boosts the idea that the universe might be a black hole. Have you ever considered that everything you know, the planets, stars, galaxies, and even you, might actually exist inside an enormous black hole? What if the universe we call home is merely the interior of a cosmic leviathan, swallowing light from another reality we could never directly observe? For decades, black holes have captured our imagination as cosmic monsters, devouring everything in their path, where even light cannot escape their gravitational clutches. But recent discoveries are forcing scientists to consider an extraordinary possibility that our entire universe might itself be a black hole. This isn't science fiction. It's a serious scientific hypothesis with growing evidence behind it. The idea sounds outlandish at first, but it actually addresses many puzzling questions in cosmology. The concept, known formally as black hole cosmology, has roots going back to the 1970s, but has gained remarkable new support from recent observations and theoretical breakthroughs. In 2023, the James Webb Space Telescope delivered images that left astronomers stunned. When studying distant galaxies, researchers noticed a peculiar pattern in their rotation, a preferred direction that shouldn't exist in a universe born from a conventional Big Bang. This cosmic alignment hints at something remarkable. Our universe may have been born spinning, precisely what you'd expect if it formed within a rotating black hole. As astrophysicist Nikodem Poplawski from the University of New Haven explains, every black hole could be a gateway to another universe. And if that's the case, our own universe could be the interior of a black hole existing in another universe. His mathematical models show how the immense gravitational forces inside a black hole could cause space-time to bounce back, creating a new expanding universe, potentially just like ours. This brings us to one of the most mind-bending concepts in modern physics: the holographic principle. Think of it as nature's ultimate compression algorithm. This principle suggests that all the information contained within our three-dimensional universe might actually be encoded on a two-dimensional surface that surrounds it, like a cosmic skin holding everything we know. Sound far-fetched? Consider this. In 2022, physicists at the Fermi National Accelerator Laboratory detected quantum fluctuations that matched predictions from holographic models. These quantum jitters in space-time align perfectly with what we'd expect if our reality were encoded on a boundary, just like the information is stored on the surface of a black hole. But how could our universe possibly fit inside a black hole? Aren't black holes relatively small compared to the vastness of space? The answer lies in Einstein's theory of relativity and its more exotic extensions. Inside a black hole, space and time behave very differently than in our everyday experience. What appears finite from the outside could contain infinite space within. This leads us to the Einstein-Cartan-Siamic-Kibble theory. A mouthful, but a crucial piece of the puzzle. This extension of Einstein's general relativity incorporates something called torsion into space-time. Regular relativity treats space-time as smooth and curved, but adding torsion accounts for the intrinsic spin of matter. When matter with spin collapses into a black hole, this torsion creates repulsive force that could prevent the formation of a singularity. Instead of matter crushing down to an infinitely small point, it bounces back, creating what physicists call an Einstein-Rosen bridge, better known as a wormhole. The other side of this wormhole could expand into a new universe, our universe. How does this relate to the Big Bang? From our perspective inside the universe, this bounce appears as a sudden expansion from a single point, exactly what the Big Bang theory describes. But from the perspective of the parent universe, it's simply what happens inside their black hole. What we call the beginning of time might just be our side of a one-way cosmic doorway. Recent research has revealed another fascinating connection: quantum entanglement. When particles become entangled, they share properties regardless of the distance between them, what Einstein famously called spooky action at a distance. In 2019, physicists Juan Maldacena and Leonard Susskind proposed that entanglement and wormholes might be two sides of the same coin. Entangled particles could be connected by microscopic wormholes. If they're right, then the quantum entanglement that seems to hold our reality together might be evidence that our universe is connected to another through a massive wormhole, the throat of the black hole we exist within. Have you ever wondered why the laws of physics in our universe seem so perfectly tuned for life to exist? If our universe is one of many spawned inside black holes, this fine-tuning might make sense through a kind of cosmic natural selection. Universes that produce lots of black holes would produce many offspring universes, passing along their physical properties. Over time, universes capable of forming stars, galaxies, and eventually black holes would become the most common type. The technologies allowing us to test these ideas are advancing rapidly. Gravitational wave detectors like LIGO and Virgo are now sensitive enough to potentially detect echoes from before the Big Bang, ripples in space-time that might have originated in the parent universe. Meanwhile, new theoretical approaches using tensor networks, a mathematical tool borrowed from quantum computing, are helping physicists model how information might transfer from a parent universe into a child universe through a black hole. Scientists are also developing new ways to search for subtle asymmetries in the cosmic microwave background, the oldest light in our universe. If our cosmos was born from a rotating black hole, these ancient photons should carry a signature of that rotation, like cosmic fingerprints preserved from the universe's birth. The standard Big Bang theory has served cosmology well for decades. It describes our universe beginning as an infinitely dense, hot singularity that suddenly expanded about 13.8 billion years ago. But despite its successes, the theory leaves fundamental questions unanswered. What caused the Big Bang? What existed before it? And why did it have the exact properties needed to form a stable universe? These questions have led some scientists to propose alternatives like the Big Bounce theory. Rather than emerging from nothing, the universe may have contracted before rebounding in the expansion we observe today. This oscillation between contraction and expansion could potentially continue infinitely. The black hole universe model offers a compelling fusion of these ideas. When we reimagine our universe as the interior region of a black hole, the Big Bang transforms from a mysterious beginning into a comprehensible physical process, the formation of a black hole in a parent universe. According to physicist Lee Smolin from the Perimeter Institute for Theoretical Physics, each black hole contains a new universe. Our universe may exist inside a black hole that itself is part of a larger universe. Similarly, all the black holes found in our universe may be portals to alternate universes. This perspective elegantly solves several long-standing problems with the traditional Big Bang theory. One of the most perplexing is the horizon problem, the mysterious uniformity of temperature throughout the observable universe, even in regions too far apart to have ever exchanged heat or energy. How could these distant regions have the same temperature if they've never interacted? The conventional answer involves cosmic inflation, an extremely rapid expansion of space-time immediately after the Big Bang. But inflation requires introducing new physics and particles that we haven't directly observed. The black hole universe model offers a simpler explanation. The uniformity exists because our universe inherited its physical properties from the parent universe during the black hole formation process. Cosmic inflation also takes on new meaning through the lens of black hole physics. As matter collapses into a black hole, space-time stretches dramatically. From the perspective of anything inside, this stretching would appear as an extraordinarily rapid expansion, exactly matching the cosmic inflation we believe occurred in our universe's earliest moments. Even more intriguing is how this theory addresses dark energy, the mysterious force accelerating our universe's expansion. In conventional cosmology, dark energy remains unexplained. But in a black hole universe model, this acceleration emerges naturally from the geometry of a black hole's interior. As matter continues falling into the parent universe's black hole, our universe, existing inside that black hole, expands in response. Think of it like blowing up a balloon. As more air enters, the balloon's surface expands in all directions. Similarly, as more matter falls into our black hole from the parent universe, our cosmos expands as a natural consequence. This brings us to one of the model's most fascinating aspects: white holes. In theoretical physics, white holes are the time-reversed version of black holes, regions where nothing can enter but from which matter and energy pour out. Einstein's equations actually allow for their existence, though we've never observed one. Within the black hole universe framework, the Big Bang itself may have been the manifestation of a white hole. The black hole in the parent universe appears as a white hole from our perspective inside, the point where all matter and energy erupted into our universe. Have you ever wondered how such a complex universe could arise seemingly from nothing? If our universe exists inside a black hole, where do you think the parent universe came from? And could this chain of universe within universe continue infinitely? Let us know what you think in the comments below. The parent universe's time flows differently than ours due to extreme relativistic effects. This time dilation means that while billions of years might pass in our universe, only moments might pass outside. The entire history of our universe from the Big Bang to its ultimate fate might be just a brief episode in the life of the parent universe. This radical rethinking of cosmology suggests our universe may be the interior of a four-dimensional black hole. While we perceive and live in these spatial dimensions, physicists have long speculated about higher dimensions. String theory, for instance, requires extra dimensions beyond our familiar three. These additional dimensions might be curled up so tightly we can't perceive them, or they might extend infinitely beyond our ability to detect. A four-dimensional black hole would have a three-dimensional event horizon, exactly matching our observable universe. The mathematics describing such an object precisely matches observations of our universe's expansion and structure. Physicist Neash Afshorty and his colleagues at the Perimeter Institute have shown that a 4D black hole could create a 3D brane, essentially a membrane universe like ours that expands because of tension in that brane. Their calculations produce predictions that align with cosmic microwave background observations better than some conventional inflation models. The concept also addresses another perplexing aspect of our universe: its apparent flatness. Measurements show that our universe's geometry is remarkably close to perfectly flat, which requires incredibly precise initial conditions in the standard Big Bang model, an extraordinarily unlikely coincidence. But in the black hole universe model, this flatness emerges naturally from the physics of horizon formation. This theoretical framework even offers new insights into dark matter, the invisible substance that appears to hold galaxies together. Some physicists propose that dark matter could be gravitational effects leaking from the parent universe, or the manifestation of the black hole's tidal forces on our brane universe. When we examine the cosmic microwave background, the oldest light in our universe, we see tiny temperature fluctuations that standard cosmology struggles to fully explain. These minute variations might be imprints from the parent universe, quantum fluctuations that crossed over during the formation of our universe black hole. What's particularly compelling about this model is how it transforms our understanding of cosmic origins. Rather than appearing from nothing, a philosophical challenge, our universe continues a process of cosmic evolution from the parent universe. The laws of physics no longer randomly emerge at the Big Bang, but are inherited and potentially slightly modified versions of the parent universe's physics. The evidence supporting the black hole universe model continues to accumulate across multiple fields of research. Perhaps the most compelling comes from analyzing the cosmic microwave background radiation, the oldest light in our universe. Recent high-precision measurements from the Planck satellite have revealed subtle patterns that align remarkably well with predictions from black hole cosmology models. These patterns show specific types of asymmetry that would be expected if our universe originated within a rotating black hole. The radiation's polarization, essentially the direction in which light waves vibrate, shows preferences that conventional Big Bang models struggle to explain but emerge naturally from black hole universe dynamics. Even more intriguing are recent observations of gravitational waves, ripples in space-time detected by LIGO and Virgo observatories. Some gravitational wave signals have exhibited unexpected echoes that theoretical physicists like Nyash Shorty suggest should be evidence of our universe's black hole structure. These echoes match predictions for what would happen if gravitational waves bounced off the boundary of our universe black hole. Of course, the theory faces significant challenges from competing models and observational constraints. Critics point out that if we truly live inside a black hole, we should observe certain telltale signs of that boundary. The absence of these specific signatures has led some physicists to question whether the model accurately describes reality. However, proponents argue that these signatures may be subtler than expected or might manifest in ways we haven't yet recognized. As Vyacheslav Dokuchev from the Russian Academy of Sciences explains, the interior of charged black holes may contain stable orbits, allowing for complex structures, potentially entire civilizations, to exist within black holes without being aware of their environment's true nature. This leads us to perhaps the most mind-expanding aspect of the theory, the multiverse perspective. If our universe exists within a black hole, and our universe contains billions of black holes, each black hole might contain its own universe with its own physical laws and constraints. This creates a nested structure of universes within universes, a cosmic Matryoshka doll of realities. Physicist Bernard Carr of Queen Mary University of London proposes that each universe might produce black holes with slightly different properties. Those that generate more black holes would produce more offspring universes, leading to a kind of cosmic natural selection favoring universes capable of producing abundant black holes. This process might explain why our universe appears so perfectly tuned for complexity in life. Universes that can't create black holes also tend to create the conditions necessary for stars, planets, and potentially living beings. The philosophical implications are equally profound. If we truly live inside a black hole, our entire concept of beginning and end requires revision. The beginning of our universe wasn't truly a beginning, but a transformation. Matter from another universe collapsing into a black hole and rebounding as our cosmos. Similarly, our universe's end may not be an end at all, but rather a transition to something else. This perspective transforms how we understand our cosmic fate. The traditional heat-death scenario, where the universe expands forever, growing colder and darker until all stars burn out, takes on new significance. That apparent death might actually be a form of cosmic maturity, where our universe becomes an ideal incubator for new black holes and therefore new universes. Our understanding of time itself changes dramatically within this framework. The physicist Carlo Rovelli suggests that time as we experience it may be entirely emergent, not fundamental to reality, but arising from interactions between quantum events. In a black hole universe, what we perceive as the forward flow of time might simply be the direction of increasing entanglement between our universe and its parent. Future experiments offer exciting possibilities for testing these ideas. The next generation of gravitational wave detectors, like the space-based LISA mission planned for the 2030s, will be sensitive enough to potentially detect gravitational waves from the earliest moments of our universe, possibly even from before the Big Bang, if our universe is indeed within a black hole. Quantum experiments are equally promising. As quantum computers grow more powerful, they may allow us to simulate the conditions at the boundary between universes, testing predictions from various models of black hole cosmology. Some physicists even propose building tabletop experiments that could mimic aspects of black hole physics through analogous systems, potentially offering indirect evidence for whether our universe behaves like a black hole interior. Advanced telescopes now under construction will allow astronomers to map the large-scale structure of the universe with unprecedented precision. These maps might reveal subtle patterns that could only be explained if our universe has the geometry of a black hole interior. The distribution of galaxies, their movement, and the way light travels across vast distances could all hold clues to our universe's true nature. Perhaps the most tantalizing question this theory raises is, what exists beyond our universe black hole? If we are inside a black hole in a parent universe, what is that parent universe like? Could it be fundamentally different from ours, with different physical laws and constraints? Might intelligent beings exist there, perhaps even studying the black holes in their universe just as we study those in ours? Some theorists suggest the parent universe might be simpler than ours, with fewer dimensions or different fundamental forces. Others propose it could be vastly more complex, with our reality representing a simplification of a richer cosmic structure. Either way, this theory transforms our place in existence from being at the center of everything to being just one link in a potentially infinite chain of universes. As we continue exploring this fascinating possibility, one thing becomes clear. The universe is stranger and more wonderful than we ever imagined. Our cosmic home might not be the isolated island we once thought, but part of a greater cosmic ecosystem of universes, all connected through black holes, cosmic umbilical cords linking realities across the void. If you found this journey through black hole cosmology fascinating, don't forget to hit that like button and subscribe to join us for more mind-bending explorations of our universe. What other cosmic mysteries would you like us to investigate in future videos? Drop your suggestions in the comments below. And as always, stay insanely curious.